So far, we've stuck to a primarily qualitative treatment of entropy, and that's awesome, but now it's time to get quantitative. According to the third law of thermodynamics, which we considered last time, a perfect crystal lattice at absolute zero would have an entropy of zero. As the substance's temperature increases, the random vibrational motions increase. This means that entropy for a substance increases with its temperature. We can therefore define the standard entropy value S0 as the increase in entropy that occurs when 1 mole of a substance is heated from absolute zero to 298 Kelvin at 1 atmosphere, standard conditions. This gives entropy units of joules per Kelvin per mole. Please note that this is an extensive property, so that the total entropy and total entropy change depends on how much of the substance you have. Anyway, these standard entropy values are tabulated in the appendix of your textbook. As with enthalpy, entropy is also a state function, and is therefore pathway independent. As a result, the entropy change, under standard conditions, for a given chemical reaction can be calculated as the sum of the standard entropy values of the products minus the standard entropy values of the reactants. And don't forget that entropy is an extensive property, so it depends on how many moles are present for each reactant and product. That means you'll need to multiply by the coefficients. Let's see if we can't use the values given to determine the standard entropy change for the following reaction under standard conditions. Go ahead and pause the video to do your calculation. And don't forget that entropy is an extensive property. So we'll go with products minus reactants, per the equation for standard entropy change. Since there are coefficients of 2 and 2 for the products, we'll double the absolute entropy for sulfur dioxide and nickel oxide. This gives us 496 joules per Kelvin plus 76 joules per Kelvin so far. Then we'll subtract the reactants, but multiply by 2 and by 3 for nickel sulfide and oxygen, respectively. So that means we've got 496 plus 76 minus 106 minus 615, which is negative 149 joules per Kelvin per mole of reaction. And you know what? I'm not surprised that it's negative, because we go from 3 total moles of gas molecules down to 2 total moles of gas molecules. So there's less positional entropy on the product side than there was on the reactant side. Here's another reaction. Calculate the delta S under standard conditions for this chemical reaction. Go ahead and pause the video until you get a solution, using the same process as the previous problems. So using the same process as before, we'll take 2 times 28 for aluminum, plus 3 times 189 for water vapor, minus 3 times 115 for hydrogen gas, minus 51 for aluminum oxide, giving us a total positive 131 joules per Kelvin per mole of reaction as a change in entropy at standard conditions. Now this is a little surprising. We would expect delta S to be closer to 0 because the total number of gaseous molecules does not change in this reaction. But instead, we get a value that's pretty large and positive. Do you have any idea what that is? Here's a hint. Compare the molecular complexity of an H2 molecule and an H2O molecule. A hydrogen molecule is just 2 atoms sharing a pair of electrons. There's no simpler molecule than that. Whereas a water molecule has another atom and a bent shape. Generally speaking, the more complex the structure of a molecule, the higher the standard entropy value. As a more complex molecule, water can rotate, bend, and vibrate in more random ways than a simple hydrogen molecule.